Cool, so welcome everyone. Our next background talk is going to be given by Peikai Qi. He's going to tell us about idele class groups for number fields and Artin reciprocity.
Yeah, thanks for the opportunity to speak here. So today we will review some statements from the class field theory. And all these statements are standard in any standard class field theory book. And you can find the reference in any number theory book. Okay, so what I will do is we first review the local reciprocity map, and then we review the process of how to construct the global reciprocity map from this local reciprocity map. And then we list some proposition about the global reciprocity map. Okay. First, let's review some statements from the local reciprocity map. So K is the local field. Then there exists a unique homomorphism from the K cross to the Galois group of KB group K. Here, this KB means the maximal abelian extension. This is standard notation. Maximal abelian extension of K. So we have a homomorphism start from the local field K cross to the Galois group, and it satisfies the following property. So first, if you have L over K is any finite abelian extension, then this map theta K induces an isomorphism. That's right. The map is A, then to theta in A, and then we restrict it to the field L. So this tells you for any abelian extension of the local field, we have a description by using the local field. Only use the information about the K cross. And what's more, under this map, we know the unit group is just the inertial group. And if we further assume L over K is unramified, and K is a uniformizer, then we know this theta K pad is mapped to the Frobenius map, Frobenius element in the field extension. So this map gives you a description for the abelian extension for local class field, and we know under this map, the unit group will be mapped to inertial group, and the uniformizer will be mapped to the Frobenius element if this field extension is unramified. So this map is very useful because this gives us a classification for any Galois group of the abelian field extension. And what's more, so by using this map, you can actually prove there is a one-to-one bijection between the open index, finite index open subset of Qi cross and the Galois group. So let's say here, the following set. Finite abelian extension. So the theory said that by using this map, you can construct a one-to-one bijection from the finite index of open subgroup to the finite index open subgroup of the Galois group, and then this is bijection to the finite abelian extension of K. So this map is, let's say, you start from a set X. X is a finite index open subgroup of K cross. Then you can use this map theta K. You can map to use this map, local reciprocity map. You can get a finite index open subgroup of this Galois group, and then you take the fixed field. So you take the fixed field, then you get a finite abelian extension of K. And let's say this field is L, let's get it as L. Then you map it back. This map, this is norm L cross. You just take the norm of L cross, and this will equals to X.
Do you take the closure data of that?
No, I don't think so. Here this map theta is continuous. Yeah. So open set will always be closed because it's finite. Okay. So this gives us a classification for all the abelian field extension of local field K. And so the next question is how about the global field? Could we construct a similar map, theta K? This map is called the local reciprocity map. Okay, I didn't say. This map is called the local reciprocity map. So the next question is, could we construct a similar map that have the same function, same property like this for global field? So naively, it's like what all other things in the number theory. If we know the local information, we can put all the local information together and we can get a global information. So we can do similar things. If we want to construct a global reciprocity map, just collect all the local information. Let keep this global field. And a notation with class and all primes corresponded to P. So you just use V or it's the same meaning. And so a natural gas for global reciprocity map will be just put all the local information together. You take the products with a place, then you map to the Galois extension of KAP. Okay. So this is a very natural guess. You collect all the local information together, and then you want to get a global information. And the issue is that if you do everything like this set here, you take the product of all KV cross with a place for K. We runs over all places of K. So this is not locally compact. So in number theory, we want our set to have a locally compact topology. So when it has a very good topology, we can say something about a continuous, something very nice. But this set is not locally compact. So the next step is we're trying to fix it. So we need to replace this infinite product as something else. Idele. So let's say some notation S is a finite set of primes or places of K. And S infinity is a set of all infinite places. So now we can define a set called AS cross as the products of sorry, I need to assume S contains all the infinite primes, the set of all infinite primes, and AS cross. We define a set AS cross as this is the finite product of KV cross and the infinite product of unit group OV cross. So we know this is a finite product of locally compact set. And this is the infinite product of compact set. So finite product of locally compact is still locally compact, and the infinite product of a compact set is still compact. So here this is locally compact. Here we take the product topology here. So this will be locally compact. And so here we only have a finite, S is a finite set of primes. So we only have a finite information, finite place. We only include this KV cross for finite place. But here we want to collect all the information about the KV cross for all the place of V. So the next step is very natural. So you just union all these sets together. So is the union of all this stuff. So if you unit all the together, so we get we can include all the information about the QV cross in our set. S runs over all the finite set of primes, include S infinity. And so by definition, because it's a unit, so this is a locally compact set. And we can write this set in another way. So you can also interpret this set as a subset inside this here, and LV is inside this OV cross for all but infinite. Finite, all but finite, many primes. So this means we can interpret this Peikai cross as a subset of this, and AV will always sit in the unit group for all but finite many primes. So you can think Peikai cross in terms of this language as well. But there is some confusion about this language because here, if you write this set as this language, you can think this is a subset of this QV cross. But the topology here is not a this is not a subset topology. So in other words, this means the topology here, Peikai cross, we are constructed from this set. We take an infinite product of OV cross and QV cross. And this topology is not a subset topology of this. This means, although this is a subset, if you take the product topology here and you restrict it to this set, this is not the topology we get here. So this is not a subset topology. So although we can view this as a subset here, but the topology is different. Okay, so now we can have some embedding. So we can embedding our K cross inside a Peikai cross just by map and A diagonally A. And we can also embedding our PV cross to Peikai cross. Just put element A in. Everything else is 1. Every other place is 1, and only in the with place we put the element A. So we have two embedding. K cross can embed in Peikai cross diagonally. Every coordinate you just put A. And a KV cross you can embed into the Peikai cross just put it in. The with place is A. Every other coordinate is just 1. So now we can fix our guess. Here we guess our global reciprocity map should look like this, and we can replace this by something locally compact. So still naively we can guess our global reciprocity map like something looks like this. And well, we can define this by because we know we can embedding QV cross inside a Peikai cross, and we know how the local reciprocity map and this also embedded to the global group. So we know how to define a local reciprocity map, and then we can embed QV cross inside AK cross, and then we can naively say we define our global reciprocity map by making this diagram commute, because we know how to map every local information, and we can embed every cross, QV cross inside of AK cross. And this looks like we got a global reciprocity map, but in fact it's not, because as I said here, although we can think we can map A in as an element here, and this element can generate all the elements of AK cross, but the topology of AK cross is not a subset topology of infinite product of QV cross. So although you can think an element here is generated by infinite product of this, but the topology, because you are taking infinite product, so this means you are taking topology, you need to take the limit. But the limit of AK cross is not the limit of this. Because when you take the infinite product, you are taking the limit of this. The topology inside here, the limit is inside here. But we need to use this topology. So this is not perfect, because when you construct this map, just to make this diagram commute, we don't know whether this is continuous or something, because the topology is very different. So although this is not perfect, but we can get some idea from this map. So for simple, let's assume L over T is abelian extension planet. Unrelified X plus V. So let's say V. Let's say this prime V, this plus V corresponds to prime P, and there is a prime, there is a plus omega theta above V, and it corresponds to a prime curly P sitting over this little p. So we can here we can have a map by respect to the Galois group of L over T, and similarly V. So we know for the local reciprocity map, we know if we have a uniformizer peg, this is a uniformizer. We can map it to a Frobenius element. This is a property of local reciprocity map. The peg is mapped to the Frobenius element. Then this means if you take any element A in the QV cross, then it should map to a Frobenius map to some power of the valuation of A. Because we know the unit group will always map to the initial group, but here the initial group is 1, because we assume it's unramified. So any element in the QV cross will map to power of Frobenius map to the power is the valuation, because the unit group always map to 1. The initial group in this field extension is 1. The unit group always map to the initial group. So by looking at this bottom map, it can give us some idea to construct another stuff. So let's go to the next topic, classic Artin reciprocity map. Okay, so inspired by the bottom map, inspired by this map, we can construct the classical reciprocity map. So similarly, that L over K is a abelian extension. Let's say it's finite. And S is the set of all ramified primes. S contains the ramified of this field extension, and also the S infinity, all the infinite primes. S contains all the infinite primes and the ramified primes in L over K in this field extension. And define I the ideal is the group generated by primes ideal of K. And IS is similar, the group generated by the ideal of K, not in X. So I is just the usual group of fractional ideal. It's a group generated by primes of K. It's a group of fractional ideal. IS is a group generated, is a subgroup of I, generated by primes ideal, not in S. So it's very natural IS is subset of I. And okay. So we can
For your I, does that include infinite spaces?
no, generated by primes. Primes ideal, okay, no. It's just a group of fractional ideal. Yeah. So here, maybe I can say one more. You can view I as a union of all IS. So yeah, you will see the relationship later. Okay. So we can define classical Artin let IS to the Galois group of L over K. If you have a prime ideal, you can map to Frobenius map. So this map is just the same script like this, because here we only can take one prime, and you can map it to the corresponding Frobenius ideal raised to some power. So in the same script, we can define the classical Artin reciprocity map by this. Let's say this is theta. We define our classical Artin reciprocity map in the same script. So here, we have do something like here. We have try to this map. You can view this map corresponding or have contains the information of the bottom map. But our goal is to construct the top map. So the next step is to connect S A K cross with IS. So let's say it again. This map contains the information like in the bottom map, but our goal is to construct top map. So we need to connect the IS with the AK cross. So this is like recall. We can write AK cross. By definition, AK cross is the union of all these S cross. And like here, you can see this I is the union of all these IS. And for AS cross, we can map to IS simply by for any P, you map to prime P to the valuation of AP. So for any element in the AS cross, you can map to IS. Just simply take the valuation of AP and raise it to the power P. Okay, you need to take product of P. Yeah. So this means we have a map, let's say, this is inside here. It's a subset. And we know we can map this to our Galois group, L4 key. So our goal is to get a map AK cross to this Galois group. But now we know how to map a subset. Here, AS cross is a subset, open subgroup of AK cross. This is like, we know how to map an open subgroup to the Galois group, but now we need to extend this map to the whole group AK cross. Good. We already know how to map a subset of AK cross to the Galois group. We need to extend this map to the whole group AK cross. So let me write again. So now our goal is to extend the map. To the whole AK cross. We only know how to map a subset to Galois group, but we need to extend it to the whole group. And now we need to use a theorem to extend it. We need to use a theorem to extend this map. So we need to first use a definition called the admissible homomorphism, and then we use a theorem about the admissible map. So definition, so a homomorphism theta from IS to any abelian group G with some topology, abelian topology group is called admissible. If for any in G, there is for any neighborhood of the identity, there exists delta greater than 0, such that the theta is never inside a K cross and smaller than delta or V inside S. So homomorphism is called admissible if for any neighborhood of the identity in G, there exists a delta greater than 0 such that the theta as in N in this neighborhood whenever A inside a K cross and A minus 1, the variation is smaller than delta. Here this it's easy to get this notation. So A is any element in K cross, so we can take a fractional ideal. But this fractional ideal, you can write this fractional ideal as a product of primes. But there may be some primes inside S, but here we need to throw away the prime S. So this notation just means you throw away prime in S in the decomposition. Of product of primes. just you can write this fractional ideal as a product of primes and then throw away these primes in S, so you can get an element inside IS. So what is good about the admissible map? Because if you get an admissible map, then you can extend it to the whole group as Aki cross. So the theorem, if theta is admissible, then there exists a unique map theta tilde from the Aki cross to the G, such that it has the following property. So theta is continuous, and secondly, theta maps the K cross always to 1. And second, the last proposition is theta A is the A O such that AV is 1 for so if you have an admissible map, then there exists a unique map. There exists a unique map theta tilde, so you can extend to Aki cross to this G, and this map satisfies the condition that theta tilde is continuous, and you can always map K cross to 1, and the last condition just said is extension theta. So the last condition just said this is the extension of AS cross to nothing special. Theta, the last condition just said theta tilde is the extension of theta. Yeah. So now, if you get an admissible map, you can extend to the Aki cross. This is
what will you erase that? So it's not clear to me why I is equal to the union of all the IS's, because S always contains the ramified primes. So for example,
yeah, you're right. Okay, yeah, this is not. Yeah, I didn't write this in the notes, but one talk.
Problem for the ideals as well. The AK is not going to be the union of all AS's because S always contains the ramified primes.
Oh, yeah.
So you can never get an element that say it's unramified.
Okay, yeah, but okay. So here, let's say, let's throw away this. But here, this unit is taking over all finite primes contains infinite primes. So yeah, this is true. This is by definition, because when we define it, S is all the finite set of primes contains infinite primes. It doesn't know about it doesn't.
But then you're mapping AS cross to IS, but theta is only defined for IS if S contains.
AS is the subset here.
Right, but on the right, you're going from AS to IS.
Yeah. Here, sorry. Here, this S is contains ramified.
That's the big problem is the definition of IS. You mean all the prime ideals in S, and then you can keep what is original on the board. It should be correct.
Yeah.
The definition of IS should be
Yeah.
prime ideals containing S. What you later on write as a map are all consistent with that.
Yeah. So if I just throw away this, so then everything I write is consistent. But
then you can't define the reciprocity map because the convenience is not all the time.
Yeah. So let's say now I just define our S is in this way. For particular S, it contains this ramified primes, and here this S is one of this S, but here this unit is S is contains all the primes.
Okay, so I mean, maybe I guess what's confusing me. So when we've defined, okay, I think I
Yeah. No question.
So the TIM in
the theorem we can pick a particular S, right? So we can call it S naught probably. That could have
Where this one?
yes. For the theorem, like could we not just take S naught to be the set of ramified primes and the infinite primes?
Okay, yeah. So for this theorem, for this whole stuff, you just need S contains S infinity for the definition, and for the theorem, this S is just use this condition. Is enough. Yeah.
I guess we are not defining this map for all S, right? Just one particular set S.
I guess the question is like if I have an element X which is ramified in X, so it's not in any of the AS crosses, then how am I defining theta? Because I can't put X into any IS.
Yeah. Okay. I know it's. So let's do this. Let's say this is S tilde, right? S tilde contains this, and let's do this. This is IS tilde, and we can also define IS and IS tilde. It doesn't matter. And here, let's say when we define a classical Artin reciprocity map, this S should always be S tilde. And so here is S tilde and this S tilde. And S tilde is just one of these S inside here. So we can also view this as a subset of Peikai Qi. Is this clear?
The bottom half here of this board, you seem to want the APs to have non-zero valuation at a finite set of primes, S tilde.
Yeah.
Which means IS tilde should be generated by those primes instead of primes outside of that set.
Yeah, because here S tilde is the product of the V inside H S tilde to V cross times. So V is not S tilde, O V cross. So if you have a primes out as S tilde is just a map unit. And here you can define.
So we are saying the definition of IS should be primes generated by primes in S instead of not. So if you cross not, then you don't need to change everything. Everything is nice.
Okay.
But we don't have any problem of that AS star because as larger the larger the better. So as contained only by prime, so what? Not a problem.
Okay.
The IS definition.
So not in S.
I know it's confusing, but it is a group generated by prime ideals contained in S, not.
And then you just remove the S infinity.
Yeah, and then everything.
Okay, I get it.
And then
Okay.
remove the S infinity as well, because now you don't S infinity.
Is this? I got confused now. Okay. I got a little confused. Okay, I get your idea. Okay.
Okay. I know that there are different places using different definition of S idele, so it's super confusing.
Yeah. Okay. Yeah. Okay. Sorry. Yeah, you're right. Okay. Here. Okay. Yeah. Start from here. For this definition of the miscible map, you can take S, include S infinity. This is enough. And for this map with it's the same. S contains S infinity because this G is any abelian topology. Actually, I should say abelian compact subgroup, abelian compact group. Okay, now, so yes, because it's the next is very nature. Our classical map is is admissible. So by the theorem, we can extend it to a map. IK equals to the Galois group of L quotient K. Good. Just by the theorem. I didn't prove this, but it's just let's take it as a black box. Theta is admissible, so we can extend this map to the Galois group. And then, because the second property, because of this, K cross always map to 1. So we can say this induces a map theta K, IK cross to K cross to Galois group of L over T. And this is called, sorry, I didn't say the name. This is a group of ideals. And this is a group of ideal class. This is like when we define class group. You have a fractional ideal and a quotient of the principal ideal. Then you call it a class. This is ideals, and then this is ideal class. So this is called a group of ideal class. And if you define the norm map, define a coordinate by coordinate. So in other words, it just defined as a product of then you can further show we can further calculate the kernel of this map. So the kernel is actually equals so if we define norm like this, coordinate by coordinate, then you can further show the kernel of this map is just a norm from above. Okay, so now lastly, we can put everything together and then get about the global reciprocity map. So finally, so this is our Artin reciprocity map, and it will give us a bijection between the finite index open set of CK. This is CK, and bijection finite index open. Okay, sorry, subgroup. And it's one-to-one correspondent to finite ability extension of K. this is our one-to-one, but it's a bijection map. And let's say if you have a open subgroup, if you have an open subgroup of CK X, you map to, by using this map, theta key, you can map to an open set, open subgroup of the Galois group, and then you take the fixed field. You take the fixed field of the theta k x, then you get a finite abelian extension of k, and then you can map it back. This is just the norm of L cross, and because we need to map it to CK right in this way, so you can times k cross and then quotient k cross. So this is our x. So this map is called the Artin reciprocity map. It gives us a one-to-one correspondence between the finite open subset of this CK and the finite index open subgroup of Galois group. So now we know that our object, our goal should be this map. In the before, we only tried to construct a map from AK cross to the Galois group. And now we know we should care about the AK cross, quotient K cross. We should care about this quotient. So our goal, so in the last few minutes, let's talk about some property about this. A property of this CK. So CK should be the central object. It should be the most important object we are looking for. So let's just talk, in the last few minutes, let's just talk about property of this CK. And so proposition, this AK cross can be written as AK S cross times K cross for S sufficiently large. Okay. And why this is important? Because you have a very natural corollary. So by definition, so if AK cross equals to this, you can plug this in. And then by the isomorphic theorem, you can write this as K cross intersect of AS cross. So if you look at this quotient carefully, you will find out that this is OS cross, the S unit group. So this intersection is just the S unit group. So you find that although we define our idele class as the AK cross quotient of the K cross, you include all the places. But actually, if your S is sufficiently large, you can just include part of the, you can throw away some places. You can also define your group of ideas by S cross quotient of S cross. So let's prove this. Proposition. So we fix a finite set. Class group. So because the class group is finitely, and class group is finite, so we can choose a finite set of primes ideal that generate this class group, because this is finite. So we can choose a finite set of primes, satisfy this condition. And we denote this as S1, denote this set, this set of primes ideal as S1. So take S include S1 and S infinite, then we claim that no, this is true. The proposition will be true. So first, easy to see that this is isomorphic. This is we call this is a group of fractional ideal. And this map is by map A inside the AK cross to it's the same map we defined before. And so because this is the ideal in IK, and we know we already choose a generator of this class group, so there exists a key inside a key cross such that a key is generated by primes in S1. So because we already choose a generator of the class group, so we can times this ideal by a principal ideal and generated by prime ideal in S1. So this tells us this VP AK is 0 for P is not in S. So, and this, in other words, this just means AK is in the OP, is in a unit group for P is not in S. So this just means our AK is in S cross, and which tells us A cross S cross K cross. Okay. Okay. Yeah, I ran out of time, but yeah, because I caused some confusion and we spent a lot of time for this confusion. Sorry about that. And so I skipped some proposition I wanted to talk about, but I think I can just 2 or 3 minutes to talk about this proposition. So here, usually for class field theory, and at least for me, I don't know how you. So at least for me, after I learned this class field theory, most of the time I don't need to use the proof. I just use the list of the proposition and just use those statements. And yeah, so you can just take every statement as a black box and just use it. And for the proof, I seldom use it because some tool like a group cohomology and group may be useful, but for other statements, I seldom use it. I just use the proposition. So I wanted to list some proposition. First, we know this global map, and I wanted to say this group, there is a compatibility between this global and the local. So this commute, and this is local. So this is just says there is a compatibility between the global and the local. And then also there is some compatibility between field extension. So if you have L omega KV is a finite abelian extension, there is a map between L omega cross to Galois group of L omega L. This is null map. This is the restriction map, and this is the local reciprocity map. This commute, and this property is called functorial. It's satisfied functorial, and this is satisfied by local reciprocity map. So similarly, for global reciprocity map, we have similar stuff. So for global, we also have LOK finite abelian extension. We have CL, CT, similarly connected by known maps, and theta L, theta K to the Galois group of LAB to L, Galois group of K. And it's a restriction map. It's the same as the local property. For local reciprocity, we also have this functorial, and for global. Okay, that's all I want to say.
Are there any questions? Then if not, let's thank the speaker one more time.